Hello everyone, I am Colin Kurz, and this is my report for Lab 3, Black Hole. This lab had two purposes. The first was to estimate the mass of a black hole, and the second was to launch a rocket ship in such a way that it would fly near the black hole. To accomplish this, two computational models were made, one that modeled a star orbiting the black hole, and one that modeled a spaceship launching off a planet orbiting the black hole. The resulting mass of the black hole and initial velocity of the spaceship needed for it to fly near the black hole were successfully calculated, and will be shown later. The fundamental physics principle of this lab was Newton's second law of motion, which states that the net force acting on a moving object is the product of the object's mass and acceleration. Derived from this law are the velocity update and position update equations, which were used in this lab. Also important is the concept that net force is equal to all of the forces acting on a system added up. In the instance of this lab, gravity is the only force acting upon the objects. Gravity is important because it governs the movement of objects in space. As a result, the equation for the force of gravity acting upon an object was used. Finally, the use of change in momentum over change in time to obtain parallel and perpendicular components of force was helpful for this lab. The first model simply shows the orbit of the star around the black hole and uses this to determine the mass of the black hole. In the scope of this model, the system was the black hole and the surroundings was the planet. To find the mass of the black hole, initial and final momentum were first calculated using velocity and mass. This, along with the given information, was used to calculate change in momentum and change in velocity. Then, change in momentum over change in time equal to net force was calculated and used to find parallel force using the formula shown earlier, which was then used along with net force to determine perpendicular force. Using net force, the mass of the black hole is calculated using the gravitational force formula. This returns several different masses of the black hole, which were all averaged together to find the real mass of the black hole, which is 9.18 times 10 to the 33rd kilograms. The second model includes launching a spaceship from a moving planet and getting it to fly around the black hole. In the scope of this model, the system was a spaceship, tracked by the magenta line, and the surroundings were the planet, tracked by the teal line and the black hole. To find the initial velocity of the spaceship needed to fly it around the black hole, four different gravitational forces were needed: the force of the black hole on the planet, the force of the spaceship on the planet, the force of the black hole on the ship, and the force of the planet on the ship. All four were calculated using the gravitational force formula. The first two were combined to form the net force on the planet, while the second two were combined to form the net force on the spaceship. Using this information, Newton's second law was used to update the velocity and position of the planet and spaceship over many time steps. A possible source of error was that the force of gravity acting on the black hole itself was not accounted for, so it was assumed that the black hole would just stay still. This might produce a gap between a real instance of this event and the data that the model predicts, for real black holes can have gravity exerted on them too. With all the pieces in place for the model, all that was left was to find the initial velocity of the spaceship as it left the planet. Through guessing and checking, this velocity was found to have an x component of negative 4 times 10 to the 7th meters per second and a y component of 1.35 times 10 to the 6th meter per second. This makes sense. For the spaceship, we need to launch to the negative x direction and positive y direction to get caught in the black hole's gravity. Some remaining questions are: what is the difference between net force and change in momentum over change in time? In a purely mathematical sense, they are identical. However, unlike change in momentum over time, force is not really a quantity that can be deduced purely from observations. All that is needed to compute change in momentum over change in time is mass, velocity, and a time interval, while the net force needs to be calculated by summing all of the forces acting on an object, which are often difficult to observe directly. This also applies to parallel and perpendicular components of both net force and change in momentum over change in time. For summing the forces acting on the object is still the first step to finding the net parallel and perpendicular forces. What if I wanted the spaceship to orbit the black hole? The initial velocity of the spaceship needed to orbit the black hole is shown and has an x component of negative 2 times 10 to the 6th and a y component of 8 times 10 to the 6th meters per second. It makes the orbit seen by the magenta path in the included figure. Thank you for listening to my lab report.